So these are example problems for the stoichiometry worksheet. So I'm going to go through several of the problems. They are labeled, they're numbered, so you know which one corresponds to the problem on your worksheet. We're going to go through how to do these problems and a little bit of background on what these problems mean. So what you're doing here is called stoichiometry, and what you're essentially figuring out is what is the relationship, the numerical relationship between products, between a product and reactant, etc. So first what you want to do is all stoichiometry problems start with a balanced chemical equation. So on worksheets like this, you may not be given the balanced equation. That's just practice for you for balancing. On a quiz or a test, though, I will give you completely balanced equations. But in the meantime, on this worksheet, make sure you check each equation to see that it's balanced. If you can balance it as I just did very quickly in your head, you are more than welcome to do that. If you need to show a little bit more extra work, you're also welcome to do that as well. So if I just added a 3 in front of the H2, that gives me 6 H's. This 2 in front of the NH3 gives me 2 N's, which matches, and 6 H's, so I know that it's balanced. You need to have a balanced chemical equation because one of the key components of stoichiometry are these coefficients here. What you're showing here is a 1 to 3 to 2 ratio. So the coefficients kind of tell you the ratio between products and reactants. So if you use the analogy of baking, usually you need 2 eggs for every cup of flour. Well, if you have 2 cups of flour and you know that ratio, you know that you need 4 eggs. It's the same kind of idea. For every 1 mole of nitrogen gas, you need 3 moles of hydrogen gas. And when you have 1 mole of nitrogen and 3 moles of hydrogen, you're going to make 2 moles of NH3. That's kind of an analogy of when you have all these ingredients, it's going to make 2 dozen cupcakes, etc. So this ratio, these coefficients, and making sure they're correct and balanced is very important here. We want to get back to our good problem-solving techniques, so we want to circle what the question is asking and underline what the question's giving. So as I read, it says, how many moles of hydrogen, circle, are needed to completely react with 2 moles of nitrogen, underline. Another step for this that I find very helpful is underneath the equation, I write what I've circled and what I've underlined. So it says, how many moles of hydrogen? That's what I'm looking for. So I'm going to write a question mark and then the unit it has asked me. So I'm going to write question mark moles under hydrogen, and then it says 2 moles of nitrogen. So under nitrogen I'm going to write 2 moles. And this visually lets me see that I'm starting with 2 moles of nitrogen, and now it wants to know how many moles of hydrogen are going to come out of that. So this visually really helps me kind of see what I'm doing here. Good thing about these stoichiometry problems is you know how to set up these tic-tac-toe boards, the factor label method. So as you know, you start with what you're given, which is what we underlined, which is 2 moles of N2. It's very important here that you write moles of N2, not just moles, and here's why. The next step is very important. It is called a mole to mole ratio. The units are going to be moles over moles because it's a ratio comparing equal things. This is why I have the N2 here. You're comparing the 2 things you're looking for in the problem, N2 and H2, and I remember that I want to cancel out N2, so it has to go opposite. That's why I make sure that N2 is written there. And I actually physically cross it out to kind of give myself a note, okay, N2's gone. Then at the top I write the other substance, the one I'm looking for, which in this case is H2. And then after I've crossed everything out, I see that my answer is going to be moles in H2, which is exactly what I circled. So whatever you end up with, the unit that's not crossed out should be the same as what you circled in the problem. Now, for a mole to mole ratio, the numbers come from the coefficients. That's why it's so important to have a balanced chemical equation. So the coefficient that's with H2 is a 3. It's not the total number of H's. It's not like balancing where you're saying, okay, there's 6 H's here, I got to put a 6 here. No, it's the coefficient in front. And then the coefficient in front of the N2, there's nothing, but we know that's a 1. Remember, 1 is assumed. So 2 times 3 is going to give me 6 moles of H2. Now, this should make logical sense. According to the coefficients, it's a 1 to 3 ratio. So if you have 2 moles of one, you need 3 times that of the other, that's what I'm showing here. Now look at the mole to mole ratio. It is like a train station. What you've been doing so far is you've been using the same substance and you've just been changing the unit. So grams to moles to molecules to whatever. Now for Stoich, you're actually going to change substances like a train station. You're getting off one train and getting on another. The way you change substances is this mole to mole ratio. So let's do one more. Remember, we're going to start with a balanced equation. So we need a 2, and a 3 to balance this. How many moles of oxygen are produced by the decomposition of 6 moles of potassium chlorate? This is where your knowledge of formulas really comes into play, because I have to know that 6 moles of potassium chlorate is this one, right under here, all right, 6 moles, not KCl, which is potassium chloride. So make sure you pay attention to that. And I circled how many moles of oxygen, so I put a question mark, moles. So what I'm comparing here is moles of potassium chlorate to moles of O2. Same process, I start with what I'm given. I make sure I use my units and my labels, KClO3. I am in moles of KClO3 and I want to know moles of O2. The way you switch substances is with a mole to mole ratio. Since they're both moles, I have to look at the identity of the substance to know that KClO3 goes on the bottom, so I can cross that out. And O2, what I'm looking for, goes on the top. The numbers in a mole to mole ratio come from the coefficients. So the coefficient with O2 is a 3, and the coefficient with KClO3 is a 2. Mathematically, I'm probably going to do 6 times 3 divided by 2, and I get 9 moles of O2. This is kind of the basic heart of stoichiometry. This is how you switch from one substance to another. You use a mole to mole ratio and you use the coefficients to switch the identity. Now once you have that figured out, you can actually start in any unit you want and you can actually convert to moles and then to the ratio. You always have to be in moles in order to use the mole to mole ratio. So if you're starting with something other than moles, you have to first get it to moles. So number 6, we're starting with an equation. Again, we have to make sure it's balanced. Remember, again, on a quiz or test, they will be balanced, but on a worksheet or a lab, they won't. It says, what volume of hydrogen is necessary to react with 5 liters of nitrogen? So I know I have 5 liters of nitrogen, and it says what volume, which is question mark, liters of hydrogen. I cannot use a liter to liter ratio. I have to use a mole to mole. So what I start with is what I'm given, 5 liters of N2, and I know that eventually I need to switch substances. Well, the only way to switch substances is to get it to moles first. So I'm starting in liters. I know to go from liters to moles, I'm going to use 22, write that again, I'm going to use 22.4 liters. Oh, I forgot the 0.4. And that's going to give me 1 mole of O2. Now this could be a confusing part because you're used to always having the moles be 1, which is what it should be. The only time it's not, the only time your mole should have a number other than 1 in front of it is when you're doing the ratio. If you're just converting between units of the same substance, it's still 1 mole always. So it's 22.4 liters to 1 mole. It's not 22.4 liters to whatever the coefficient may be. The only time the coefficients come into play is in the mole to mole ratio. So right now I'm in moles. As soon as you get your substance into moles, the next step is always the mole to mole ratio. We're always hitting the train station and changing tracks. So I know N2 goes on the bottom because it's opposite to cross out. The substance I'm looking for, H2, goes on the top. This is where the coefficients go. Nowhere else except the mole to mole ratio. So the coefficient with H2 is a 3 and the coefficient with N2 is a 1. Now it says my answer needs to be in liters. Right now I'm in moles. I'm in moles of H2, so I'm in the right substance, wrong unit. So all I need now again is to change it from moles to liters using that 22.4 conversion. Notice I'm not changing my H2. It's going to stay H2, and it's 1 mole because I'm just converting within the same substance. I can either multiply the top, divide by the bottom, or I can do it as I go and do 5 divided by 22.4 times 3 times 22.4, and I'm going to get 15 liters. It's your choice whether you want 15 liters of the substance or not. Eventually you're going to have to write it of the substance just because you're going to have to know what that is. Okay, let's go on to another one. Now we're starting in a different unit. It's all the same process. Get it to moles, do the ratio, get it to whatever unit you're looking for. So we need to start with a balanced equation. So we have a 2, and a 3. So it says how many grams of potassium chloride are produced if you have 25 grams of potassium chlorate. Again, we have to know our names to know that is 25 grams, and this is what I'm looking for. Start with what I'm given. So I'm 25 grams of KClO3. I know eventually I'm going to have to change substances. The only way to do that is with a mole-to-mole ratio. The only way to use a mole-to-mole ratio is to be in moles. So my next step is to convert grams to moles. This is a ClO3 using my molar mass. The molar mass of KClO3 is 122.55. Cross that out. Now I'm in moles. As soon as I'm in moles, I know I can do my mole-to-mole ratio. KClO3 goes on the top. Old substance is gone. New substance, KCl, goes on the top. Numbers come from coefficients, so it's actually a 2 and a 2. Now I understand that this can be simplified to 1 to 1, but I think you would get confused about where the numbers came from. So I would just keep it matched. I wouldn't simplify, I would just leave it as 2. If I stopped here, I'd be in moles of KCl, but the problem says I need grams. So to do that, I simply use molar mass conversion again, molar mass of KCl, which is 74.55, and I'm going to get 15.21 grams. So one thing that can be confusing with a mass to mole problem is you might have two different molar masses, and sometimes that can get confusing about which one goes where. Just remember they should match vertically. So the molar mass that is on the bottom here should be the molar mass of the substance on the top. Molar mass that's on the top here should be the substance on the bottom. So just remember to match them vertically. Let's do one more of these. Balance first. It says how many grams of hydrogen are necessary to react with 50 grams of nitrogen. So I have 50 grams of nitrogen, and it's asking about grams of hydrogen. Start with what I'm given, grams of N2. I'm in grams. I don't need to be in grams, I need to be in moles. So I'm going to use the molar mass of N2, which is 28.02, to go from grams of N2 to moles of N2. As soon as I'm in moles, I can use a mole-to-mole ratio. I know N2 is going to go on the bottom, so it cancels out. My new substance, which I can look up right here, H2 goes on the top. Coefficients, 3 with an H2, 1 with an N2. If I stopped here, I'd be in moles, but I don't want to stop there. I want to be in grams. So 1 mole H2 on the bottom, and the molar mass of H2 on the top. Remember, match vertically, match vertically. Do my math, and I should get 10.81 grams. Okay, next one. Now we're going to mix problems, and these are more likely what you'll see on your quiz or on like a normal stoichiometry problem. Mixed just means the units are mixed, so you won't be starting in the same unit and ending the same unit. Everything else is the same. So we're starting with a balanced equation, and I'm just going to read, circle, and underline. What volume of NH3 at STP, remember STP just stands for standard temperature and pressure, it's just a set of conditions, is produced if 25 grams of N2 is reacted with excess H2. This excess H2 is just a distractor for now. So it says what volume, which is going to be in liters, so question mark liters, and 25 grams of N2. So now I got to really pay attention to what I'm doing here. So I'm starting in grams of N2. I'm going to have to switch substances, so I'm going to have to be in moles to use a mole-to-mole ratio. So my first step is to change grams of N2 to moles of N2 using the molar mass. As soon as I hit moles, I know I can go mole-to-mole ratio. I'm at the train station. I switch substances. N2 is now gone. The one I'm looking for, NH3, is now here on the top. Mole-to-mole ratio includes the coefficients, so NH3 has a 2, N2 has a 1. And then I have to check. It wants my final answer in liters. So I'm going to go moles to liters. Using 1 mole equals 22.4 liters. Pay attention to the ones. The only time the coefficients come into play is the mole-to-mole ratio. Multiply the top, divide by the bottom, or do it all in one step, and I should get 39.97 liters. So you see the pattern's still the same. Even if you're changing coefficients, if you're using different coefficients, it's still the same pattern. Balanced equation for 17. It says if 5 grams of KClO3 is decomposed, what volume of O2 is produced? So again, KClO3 is 5 grams, volumes measured in liters. Start with what I'm given, 5 grams of KClO3. I need to eventually get it to O2, so I first need to go from grams to moles, dividing by the molar mass. Remember, don't get confused about what molar mass to use. It should match vertically. The molar mass here should be the same for the substance at the top. I'm in moles. My next step will be a mole-to-mole ratio. KClO3 goes on the bottom so I can cancel. New substance goes on the top, O2. O2 has a 3 coefficient. KClO3 has a 2 coefficient. Then I double check. My answer needs to be in liters. So I'm going to go take that moles of O2, change it to liters of O2 using 22.4, and I'm going to get 1.37 liters of O2. So what you should have noticed here is there is a pattern. There's a pattern to this. With stoichiometry, the most important, the middle, the central, the most important thing is the mole ratio. That's the middle. You can start in any unit you want. You can start in liters, you can start in grams, you can even start in molecules if you want. But in order to get this mole ratio, you have to turn whatever unit you start in to moles, and then as soon as you're in moles, you're in the mole ratio. Then after that, you can turn it to liters or grams or molecules or whatever it needs to be. So whatever you start in, your first step is to get it to moles. If you're in moles, you're skipping this first step. Once you're in moles, the next step is automatically the mole ratio, and then after you're in the mole ratio, you turn it to whatever unit you're looking for. Again, if you're looking for moles, then you just keep it as the moles here. You can also maybe start in milliliters, kilograms, whatever it is, or end in milliliters, kilograms, etc. But it's all going to end up with eventually you need to get your answer into moles in order to switch substances at the mole ratio. This is the key, this mole-to-mole ratio. It's going to be moles over moles, and it allows you to switch substances. It's the train station. That's where you switch from one substance to another.